Hi there, welcome back to the channel. Welcome to the next episode in the Back to Basics series, showing every step in the restoration process of a tube radio on this Not Mende. And in this video, I want to cover the preamplification stage. I want to talk about the signal directing, the signal sourcing that finally gets through to the preamp and the power amp and then obviously the speaker. And also I'm going to go into the tone shaping components or parts of the circuit, which are very interesting because they are almost unique to these old radios when people wanted distortion to get the sound to sound better. Nowadays, it's the other way around. But I'm taking this one step at a time, and there's quite a bit of schematic work on here. So if you don't want to follow that too much, just do a bit of skipping forward. Put me at 2.5 times speed or 2 times speed on your player. I sound a lot more intelligent that way. So if this sort of thing is interesting to you, stick around and enjoy the video. But before I carry on, I just want to thank the sponsors of this video, PCBWay. They're the guys I go to for all my PC boards and lately for quite a bit more 3D printing than I was expecting. The results have been phenomenal. Very happy with the turnaround times. As you can see, prices are exceptionally good. They're actually running a design competition, which is the KiCad Open Source Design Contest. If you follow the links in the website, take you to the competition page. You'll see the rules, submissions, discussion, and so on. As you can see, it's around 2 main themes, the communications project or an automation project, and then the awards, the prize is also listed on here. So whether you're looking for PCBs, 3D printing, or even just going to the store and see what some of the great kits and modules you can buy from them, I'm sure you'll find something for your needs. Let's start by clarifying a bit of doubt that was created with this circuit over here. I probably didn't explain this as well as I should have. In fact, I hadn't researched it as well as I should have, which means I created more confusion than it was worth. I am sorry that I caused a few of you to have sleepless nights. I really am. But let's have a look at this. Now, it's actually simpler than it looks. What we have here is a situation where this resistor here gets shorted out in the event that you do not have FM or pickup. It wasn't bass, it was pickup. I got that wrong when I read the broken, shattered faceplate, so I apologize for that. So what we have is a situation where if you do not have FM or pickup, then these two guys are shorted, which means that that capacitor there goes straight to B2+. In other words, that the high frequencies are effectively shorted out to a low impedance path, which is the second B+. So those frequencies go nowhere. When you have FM or pickup selected, one of these opens up, which means that this resistor now comes into play, which means that the audio no longer escapes to ground through the power supply, but indeed goes through to the electrostatic tweeters. So effectively what we've got here is when we have FM and pickup in the off position, in other words, they are not selected, then these switches are made. These are normally closed. So when you select, for example, FM, look what happens. See that? I'm just selecting FM. See the switch? Now what we've got is this path has been opened and this resistor comes into play. So the audio, the high frequencies, actually goes to the electrostatic tweeters. Now if we have FM not activated, but we activate the pickup, same thing happens. See that? Activate pickup. That switch opens. That's on the pickup block of switches, C2 and C3. And that path is now broken, which means this resistor comes into play as well, which means high frequencies go to the tweeters. So I like to do this because it does make it easier to understand. You know, you can switch on and off, you can switch on and off, and it makes it a lot easier to see what is happening. These switches are indeed just, they're just connected in series. It's not a big mystery. It's a lot more mysterious when you're basing yourself on an explanation that I gave, which was essentially incorrect. So what we want is this path broken when we want the high frequencies to go through to there, like with FM, which has good quality audio, and with pickup, which has essentially good quality audio as well. There we have it. That's that mystery solved, I hope. And now we're ready for the next stage, which is, or should I say the previous stage, which is the preamp. And for that, we're going to add another tube. The preamplifier tube, which is actually a multi-purpose tube. This tube is very interesting because it has, besides the triode, which we are using as a preamp, it has 3 diodes. And we'll see later why those 3 diodes are in there, but this is quite a magical tube, very useful, multi-purpose, and after cleaning the pins and cleaning the holes there, we can plug it in. Now we've got a preamp and power amp, and we are making a little bit of progress, but just so I spoil your fun a bit, let's go look at the theory. Let's look at the schematic. Right, we're still with a rather simplified version of the tone section of the preamp, because if I do show it, you can see there's still a lot more down here. But for now, let's hide that. And this is what we're looking at. Now remember, we've also checked quite a bit of this. We've checked all this in green. So we really are interested more in this section down here. And what we're looking at, because we're looking at an audio stage, because we're looking at a preamp stage, we want to see what the audio path is into this preamp section over here. Now, before I go any further, let me explain what this is doing. You can see this is rather a complicated tube, but it's actually quite simple when you break it down. You've got an anode, a grid, and a cathode of a triode over here. That's all this is, a triode. It's the same as a half of a 12AX7, you know, an ECC83 or 12AT7 or 12AU7. It's just a triode, all right? And here we've got a diode. Okay, now that's anode and a cathode. The anode there, cathode there for a diode. This diode is actually completely independent. It's got separate pins. And then we've got another 2 diodes over here in which the cathodes are actually joined together. So the anodes are separate, but the cathodes are joined together. And these 2 cathodes are joined to the cathode of the triode as well. As you can see, there's a wire in there, there's a line in there. And this goes to ground, right? So this is our triode. We're only worried about that section over there, okay? And this is the triode that is doing preamplification of the audio that comes in here before it goes out there, which then goes through all the stuff we described to the power stage. But how does this thing work? Well, it's actually a very straightforward triode amplification stage, a voltage amplification stage. These triodes don't have much power, they don't carry much current, but they do amplify voltage. And it's always nice to look at what a textbook case would be for this kind of stage. Let's look at that. Here we have the triode amplification stage in a rather more readable fashion than what we have over here. And it is actually the same. If you start following this around, you'll see it's the same. Let's take it one step at a time. We've got our triode over here. And this triode has actually got its cathode connected to ground, which means we need some way of biasing it. Remember we discussed how this thing obtains bias by the current that goes through that cathode resistor, right? Now there's no cathode resistor here, which is a little bit unusual. So this thing is not cathode biased, which means that if this is at 0 volts and if that was at 0 volts, this would be almost wide open, right? So it wouldn't help us at all. It wouldn't work as a triode at all. However, there is another way of biasing this. Actually, there are more ways, but one way of biasing this is to take advantage of some electrons that do hit that grid flying out of the cathode. Remember, this will be a positive voltage. It's coming from an AB+, so it's a positive voltage. This is ground, so electrons get attracted from there to there, okay? They get attracted and they would normally get stopped by a negative voltage over here. They'd be pushed back into the cathode. Wouldn't allow as much to go through to the anode as would want to, right? But in this case, what we've got is we've got ourselves a grid which is getting hit by some electrons. And what happens is those electrons are going to go somewhere, and where they go to is ground, right? They're going to find a path to ground. I mean, it's very small current. But if you've got a very, very small current going through a very, very, very big resistor, you get a voltage. And this is exactly what happens. This resistor 172 is actually 10 mega ohms in this case over here, which we'll check now. This thing, I've checked the schematic, it's 10 mega ohms. Now that is a huge resistor. So no matter how small the current is that finally gets, or the electrons that get released here creates, it is still quite a significant voltage, probably about 1 volt or something, which is enough to bias this. 1 volt, in other words, a negative voltage, right, across from the grid to the cathode to give this some sort of control. Now, this is exactly what we have here. We've got our triode there. We've got our cathode connected to ground. There's our cathode. That cathode there goes down there to ground. So it's exactly the same. We go to the anode and we've got a resistor here, and that's exactly what we've got there, resistor 144. That's our anode resistor, our load resistor. This here is considered to be a low impedance ground point, so like a supply, so we don't count that. This resistor, as I said, was to get rid of high frequencies, to basically drain them off. But we also have this path here, from there to that capacitor, and that capacitor is the one where the audio is going to go through. It's a DC blocking, but it's a coupling to the PA stage. And that's what this capacitor is here. So we've got the same layout as we have here. It looks completely different, but it's exactly the same. Now in this case, we've got C172, which is separating the preceding audio from the grid. And if we follow this over here, we follow this grid line, there's C172. So that's that capacitor. And it took me a while to find the bias because I wasn't looking properly. I was trying to find the bias for this because I couldn't see how this was biased. I forgot this thing's got a resistor down here. That's that 172 that I mentioned, which is 10 mega ohms. So this is the entire preamp circuit. It's a coupling capacitor, a bias, it's a grid leak bias resistor of 10 mega ohms, and it goes to there, and then the triode does its job. So that's basically what we've been looking at. So now we're interested in checking how the audio path follows the various lines over here. How does the audio path get managed in order to get the audio to go into the triode, into our preamp? Remember, what we're trying to do is we're trying to get audio from this point into the grid, which then does its job and sends the audio forward, having amplified it. We've already checked this section. It's all painted green. So we've done that. All we're interested in is this part over here, really, right? So let me hide that green so we don't get confused here. And this is what we're looking at. We're looking at how the audio gets from this point to that point, because that really is the preamp audio path going into the grid. If you follow back, we've got the bias over here. We've got that the coupling cap over here. This is a very important resistor as well, because if this is leaking DC, that could be a problem as well. Not as bad as that one, but you should also check that first. Okay, so we've got a very important capacitor to change here. And really what we're interested in is finding out how the audio gets to this point. And it gets to this point by a wiper, or through a wiper of a volume pot. This is our volume pot over here. And the volume pot really gets its audio signal to the top of the volume pot, and the bottom goes to ground. Usually ground would be right here. In this case, we've got a resistor over here, and we'll see why this resistor is here. This is to allow feedback, tonal shaping, negative feedback, but we'll see that shortly. All we're interested in is, we know that the preamp sees this. How does the audio get to this point? Okay, so let's look. We've got three options over here. We've got these two switches in the general proximity of where we think the audio is going to or coming from. So let's just label them. If we look at the coding on here, we find that this is the FM switch and this is the pickup switch, the phono. Now, what happens when we have the phono on? We switch phono, we click phono. This is what happens. See that? Our phono is now on. That means that the radio is, or the preamp section, should get audio from the phono input over here. And does it? Well, let's follow that. Audio comes in here, goes through that switch which is now closed, that part of the switch which is now closed. It goes through there, through that switch which is normally closed when FM has not been depressed, right? This switch will change when you push FM, but you haven't pushed FM, you've pushed phono, TA. So there the audio goes through, goes in there, goes through there, and it gets to where we want it to be, to get selected, the level you want, the volume you want, and going into the preamp and doing its business, right? Now that is phono on. Back to a situation where we don't have phono on and we want AM. Now AM doesn't require this switch to be made or closed, or this one to be closed. It's actually activated further upstream. But what is its audio path? This is the audio path for AM. AM comes from here. We'll see the backstream later. but it comes from here. It goes through that switch, which is closed because this is not selected. It goes through that switch. This side is closed because the FM is not selected, and it gets to the top of our pot. So we've got our source for the audio, in this case, to go into the preamp. We've got one more step to go, and that's when we have FM selected. When we click FM, that's what happens. It's unselected, click FM, that's what happens. And here's our audio path. But FM comes from here, through that switch, which is now closed, and down to our desired entry point into the preamp stage. That really is it. So when we look at this section over here, it is very, very simple. It only becomes complicated when you start looking at this. And even that is not that complicated, believe me. You'll see in a minute. So what do we have to restore or repair or replace to finish our preamp stage? There isn't that much to check, because what you can do is you can use, to test the preamp stage, you use the phono input. It's the most logical input of audio that you have. You know, you don't want to, you haven't got your FM radio working yet. We don't even have the tubes in there, or the AM, but we do have a phono socket at the back, and that's usually the first point that we use as a test for our audio stage, meaning the entire audio stage, meaning preamp and power amp. So we can feed a signal in there, it'll go down here, we can check if these switches work, we can actually check if these switches work, because we can click FM and see that the tone goes away. We can then check this capacitor, which we probably will need to replace, and we have to replace that capacitor, and we can check the pot, we can check these resistors, and we have a fully fledged preamp stage to work with. So let me go and check these capacitors and see if we need to change them. Okay, let me show you how this thing can confuse you. I've just been caught out by a trick that I've fallen for in the past. So let me show you with the multimeter what it is that they sometimes do to catch you out. I'm going to put one side of the multimeter to the input of the phono. That's this over here. The other side is ground. And I'm going to follow the signal. It goes to the pickup switch. So if I go to the pickup switch at the back here, I expect it to beep somewhere. Yeah, and it's beeping there, okay? Now, this is the one that takes it off the pickup switch. So there we go. That's the switch that we see there. This is D7 and D8, okay? And then there's a little wire here that goes to the FM switch. This here is activated by the FM as well, although the FM is on this side. That's activated by the FM as well. So if I select TA, I'm following TA, I can get to here, and this switch has contacts on both sides, so I can get it to this side, and it's on here. It goes to this capacitor, right? You can see that 0 ohms, or close. Then it meets a capacitor. That makes sense, because on our schematic, we can see that it should meet capacitor 171, C171, which should be this guy over here. But then I saw something strange. C171 goes to the EL84 tube, which just doesn't make sense. I've taken the multimeter now to the other side of this capacitor, because we can't measure resistance through a capacitor, and I see that it goes to pin 1 of EL84. Can you hear that? And this then goes from here to 2 other places, and one of them is the pot up here. This is the volume pot up here. Now that confused me. There are a few other things going off here as well, pin 1, but that's got to do with the tone shaping, which we'll get to in a minute. That confused me until I looked at the datasheet for an EL84. And when you look at this datasheet, you see that pin 1 is not used at all. It's not connected to anything. So what they've done is they've used pin 1 as just a convenient tag point, solder point. And that can confuse you if you don't know what they're doing, because this doesn't make sense. If you look at this and you think, you know, what the hell is this doing going to the output tube when it's actually should be going to the pot, that could confuse you. They do things like that just to catch you out. I'm sure they do it on purpose. So anyway, it gets to there. I've got this in the right place, and if I follow through, it goes to the volume pot. There we go. And if I go to the wipe of the volume pot, and if I twiddle the volume pot, you see it's going to 650 kilo ohms, and the other way goes to almost 0. Okay, Now it's actually in reverse because I'm measuring from the top of the pot to the wiper, so I'm turning clockwise for 0, counterclockwise for the highest resistance. And if I measure to the other side of the volume pot, that's the total resistance, okay? The volume pot is 620k or so. Now, I'm not too worried about the exact value because there are a lot of other resistors in place here, which we'll see when we look at the tone shaping. So this thing does throw the values out. So that is the first capacitor that I need to change. That is C171. And if I go to the volume pot from the wiper, I believe it's that guy over there, which is actually, yeah, this is a shielded capacitor. I think the 10 meg resistor is inside. And if we look at the schematic, we can also see that it's got a shield around it. This dashed line here shows that it's inside some sort of shield. So I think that is something we're going to have to rebuild. Yep, I'll take it out and we'll have a look at it. Here's that component that I removed, and as you can see, it actually says 0.01 microfarads, so 10 nanofarads, plus 10 megohms. That's that capacitor and resistor. The capacitor and resistor have a common connection here, which goes to the wiper, and then the capacitor goes on with a signal, and that there is the ground, and that's also the connection point of the other end of the resistor. But there's obviously a shield around here which they've also connected to ground. Now we're going to do exactly the same thing. Let's just check what this thing measures like. So we should measure 10 nanofarads there. We're getting 62. And we should measure 10 meg from that end to here. And it's actually seems to be open. That resistor is open. It's completely gone. So that's what we're going to do. We're going to rebuild this, and it's fairly easy to do. Here I've got a 10 nanofarad capacitor, and I've got a 10 megohm resistor, and I've connected those two sides together. So what I need to do is I need to make sure that this section here is perfectly insulated, because this guy is going to go to ground. This guy is the end of the cap, so that's going to get insulated as well with heat shrink. But I want this part to connect to a shield that I'm going to put around here, which means this insulation mustn't let the shield touch this end. And then I connect this to the shield, and that goes off to ground as the other component was doing. Should be fairly simple. I'll put some heat shrink on these ends first. Right, so the heat shrink is protecting the inner wire, and I've kept it green because that's what the original color was, but it still doesn't protect that little bit there, so I need to protect this section of the resistor. And here we are. I've protected that from shorting to the shield that I'm going to put over here, and the rest can touch the shield because that's going to be ground anyway. This inner one must not. So now I'm going to get some metal tape. I think I've got some copper tape, and I'm going to wrap it around there, and then I'll show you, and then after that I'll be covering this whole thing with heat shrink anyway. Well, admittedly, this looks like a bit of a mess, but believe me, it'll look good in the end. The resistor wire has been bent back, and I've soldered this, which is now the ground lead, and it's soldered to the copper wire or the copper tape. I've made sure that there's no contact between the copper tape and that end, or copper tape and that end. So now we just need to put some more heat shrink on. By the way, this one's actually better than the other one because I've put the copper tape along the wire. So this lead, which is where the audio signal is coming from and which is getting fed to the rest of the circuit is actually shielded to there as well. And our capacitor, some strange reason, our component here, the original, had this huge wire that went and sort of bent back and then was soldered to the wiper of the pot. So I don't know why they put a shielded component set here and then basically left an antenna in place. All right, let me finish this and show you what the result is. Here we go. 0.01 microfarad capacitor plus 10 meg ohms. There's the one that comes from the wiper. That goes to ground. That's the continuation of the signal. I'll put this in, and that's one more task concluded. So what we've got now is we've got a little bit more checked because we've done that section over here. As you can see, what I've done is indicated that I replaced that capacitor, and that's resistor. So that's in place. This is starting to come together, but there's one more section here that I just want to get out of the way very quickly, and that is this little bit over here. We're looking at the DIN socket at the back. This socket at the back, it's a DIN socket. It's for a tape deck and tape player. We've got the pin 2 reference to ground, obviously. And then we've got this pin here, that pin there. Now that pin there is actually a tape output. In other words, you see this line coming from the top here. It's coming from the phono input, okay? Now imagine that you do not have a phono on, but you connect the input to there. Well, this means that whatever is coming out of pin 3 or the respective signal at pin 3 is going to where the phono input was. So it is replacing the phono input. In other words, you can use this as an alternative input to your phono. When you select phono, this switch is made and whatever is coming out of here goes through, replacing the phono signal. So that's the one that'll come out of your speakers. This one here is different. This is a record signal. And the way we know that is, you see where it comes from? It comes from here. So whatever signal, wherever it's coming from, is arriving at the potentiometer before it is reduced in volume, up there, here. It goes through that resistor, which is 1 meg, and then there's that resistor, which is 100K. So this is just a potential divider. It's reducing the level and giving it a ground reference, and then that goes into pin 1. So whatever you are listening to, whether it be AM or FM, or even phonograph coming through there, you can record it onto your tape deck. So here's our DIN socket. We've got pin 2 is the ground, the middle, going to a common ground down here that's shorting all these together. Pin 3 is this one over here, and this one over here is the one that goes to the connection that continues from the phono input, okay? This would be the tape in if you weren't using a phono input over here. And then pin 1 on the schematic is this guy over here, which has 2 resistors on it. One resistor, the one at the back here, is 100K, and it's going to ground as well. And that's resistor 181 on our schematic. No problem, I've measured it, it's fine. This resistor in front here is resistor 192. It's 1 meg, and it goes to a solder joint or solder point over here, which then goes off in a shielded cable, and it goes up here to pin 1 of that EL84 tube, which is being used as a solder tag, solder connection point, where this capacitor joins it. And that's exactly where it should go, because then it goes off to the pot. And if you look at the schematic, that's exactly what we have. So these lines here can now be painted. And we've now got one more issue covered on this schematic. And we can now move on to one of the really important or really interesting sections of this circuit, which has to do with the feedback from the speaker itself. This is a really interesting topic. That's what we're going to cover next. What I'm going to show you here is what happens to the signal between the time that it goes into the amplifier stage and when it comes out of the speakers. What we're seeing on the scope there is the input signal. Now I've got a 1 kilohertz signal. It's 1 volt peak to peak or RMS, I'm not even sure. But that's the yellow trace that you see on the screen there. Now I'm also monitoring the output at the speaker itself, and I'll put the speaker on so you can hear it. There it is. Let me put it on dummy load. Now if I put the volume up, this is what happens. This is the output at the speaker that you're seeing there. That's the blue trace. And obviously it's going up and down because I'm playing with the volume control. Now, what I'm trying to show you here is that the two signals are practically 180 degrees out of phase. They are inverted, as it were. So if I take this one down, And if I take this one up, they are almost 180 degrees out of phase. Now, obviously, you can still see me playing with the volume control, and the output's going to swing up and down depending on what volume level I'm giving it. But the phase is staying practically the same. Now, what this means is if I take some of this output signal, this blue trace, right, and I bring it back to the right position in the tube, I can get this to subtract from the top one. I can create a negative feedback. Now, this is rather complex because what we're getting in the various phases is that the signals invert. So the signal going in, the yellow signal, when it goes into the preamp input over here, by the time it comes out of the anode as an output signal, it's been inverted 180 degrees, okay? Then that goes through a lot of stuff and it goes into the grid of the EL84. And when it comes out at the anode, in other words, to drive the output transformer, it's inverted again. But then you can also invert the speakers, depending on which of the secondary winding sides you connect to ground, you can invert the signal. You have to be very careful if you replace an output transformer that you get the phase right, because otherwise, instead of negative feedback, you get positive feedback, and positive feedback will blow your ears out. It'll just start howling. It gets worse and worse and worse and worse, sometimes incredibly fast. You don't even have time to stop this thing from self-destructing. So negative feedback is a control mechanism. Positive feedback is pure havoc. You don't want positive feedback, right? I know there's actually a radio where Philips uses positive feedback, and on oscillators you use positive feedback, but not in an audio circuit like this. Okay, so what I was trying to show you here with the scope traces is that the output signal reference to ground, both these are reference to ground, the chassis in this case, is inverted when compared to the input signal, that yellow trace over there. Now, this is important when we look at the schematic and what all those components are doing to shape the tone when it comes back from the speaker to the volume pot. Remember, there was a little resistor at the bottom of the volume pot, right? It didn't quite go to ground. Well, you'll see now why they do that. Let's have a look at the schematic itself. This is where we were, and we'd finished this section. Now we can go one step further and look at what it is that we've hidden before. That is all this stuff here. Now, you can see this is still all related to the audio. The radio works back here, right? This is all audio, okay? Now, we'll take this in two stages. One has to do with feedback from the speaker from this point over there that comes back to this point over here, that volume pot that I mentioned, okay? The other stage, or the other section of this, has to do with the influence that all these components have on the actual volume control and various internal taps that this volume control has. That we'll go into shortly as well. But we're interested in this section over here, the feedback section over here. So again, I isolate it. As you probably know, I'm a fan of this. Makes it a lot easier to understand. And also it's easy to understand because some of the concepts that we see here have already been covered or been discussed in the previous stages of the audio. So let's focus in on this. First of all, just remember, this signal is coming back from the speaker, from the actual speaker. The speaker is connected to ground, and this is the other side of the output transformer to the speaker. So this is our signal coming out here, right? It comes down here and it goes to there. Okay. So what we've got is feedback. We've seen this is the inverse. This is a reverse signal, an inverted signal compared to the one that's coming in to the volume pot over here. Okay. But the point is, you're not just doing it for all frequencies. You are doing it for selected frequencies. So what is happening is part of the signal is coming to the bottom of the volume pot. Now, if I have a signal going up here, right? Sine wave going up here, at the top of the volume pot. And what's coming back is that same sine wave, or a portion of that same sine wave that's going up. But down here it's going down, it's going to subtract. Or is it going to add? You know, when you subtract inverted signal, you're adding it. So what's going to happen is the result will be a reduction of that sine wave going up. That'll end up being across this potentiometer. That will end up being fed to your preamp. Okay? So what you're doing, whatever you put on here is going to be deducted. Again, you've got to look at phase, but let's call it deducted from what's coming in at the top. And the more you put on here, the more reduction you're going to get going into there. So the more, let's say, high frequencies I bring back to this point over here, the less high frequencies are going to go into that pot. You increase there, you decrease there, you increase there, you decrease there. And that's why a feedback circuit works like this, okay? And the reason it works is because the signal is inverted. But let's look at the frequencies. What are you doing over here? Well, if you have all the frequencies from 20 hertz to 20 kilohertz coming out of your speaker, okay? Let's say that this is a very, very good output transformer and you're getting the full audio range, which you will not. But let's say that you are. When it gets to this point, we see a very similar circuit to one we saw previously. A capacitor in parallel with a resistor. You remember this over here? You remember that? A capacitor in parallel with a resistor? What do we say happens here? All high frequencies get through and low frequencies get sort of impeded depending on where this variable resistor was set. Well, here we don't have that. High frequencies do get through this capacitor, but low frequencies get reduced, right, by the fact that there's this resistor on here. Remember, high frequencies can easily jump across that capacitor. Low frequencies cannot. They get sort of slowed down, dampened when they try and get through here. So what you've already got at this point is a version of the output that is scarce on low frequencies. So you've got more high frequencies here than low frequencies when compared to that signal over there, the original signal coming from the speaker. So you've reduced your bass content at this point. Now, forget about this. This is on the outside for now, but it's basically the same thing. You are going to reduce it further, but it's going to reduce everything further, high frequencies and low frequencies, because it's just a resistor which can be shorted out. So let's assume it's shorted out. Then you get to this point, and what you've got here is another resistor, but now you've got another circuit that we saw up here. Remember this circuit over here? A capacitor that meets a resistor? What do we say happens? What happens is that the high frequencies want to escape. Low frequencies can't really get through, but the high frequencies can, and they want to escape, and suddenly they meet someone saying, whoa, not all of you, right? Slow down, not all of you. So this creates a high frequency cutoff shelf, as we saw with those simulations, the LT Spice simulations that I showed you. So this is a high frequency cut. That is a low frequency cut. This is a high frequency cut. So we get back to here, and this is what we've got. We've got a high frequency cut. So what are we doing? We're reducing low frequencies here. We are reducing high frequencies here. So we're sort of creating a bit of a hump in the middle, aren't we? Depending on where the cutoffs, these RC circuits are. But that's what's happening. You are tailoring which frequencies can get back to this point over here to be deducted from the input signal so that they don't get produced so much at the output again. See how that works? Yeah, sometimes I do. Sometimes I don't. With feedback, it's like that. Feedback is like watching a movie where you go back in time. Time travel? I've always hated time travel movies because I get myself so mixed up because you start questioning that whether things would have happened. You know what I mean. If you don't lose sleep over it. But this is what happens with feedback. You are tailoring which frequencies are allowed to come to this point to then go to this point to be removed from the spectrum that's being amplified. All right? There's one other thing to consider. This would all be nice if the output signal was always the same. You could say, right, let's do a simulation where the output signal is constant, but it's not. So the amount of feedback that you're going to get is volume dependent. Do you see what I mean? The frequency shaping that happens with this circuit, reducing bass, this one cutting off some of the really high frequencies, and then they go back through this capacitor and they get reduced or removed from the signal that's trying to get preamplified. That is not constant. Frequency-wise, the shape will be the same, but the amplitude will change. And that amplitude might not be changing. That might be a fixed sine wave coming in, like I was showing you. But even if it's just music coming in, you're not playing with the volume of the signal coming in, but But you can play with the volume of the signal coming out, which means that the amount of signal that's fed back will depend on your volume level. And this is also important because there are certain things you want to do at high volumes that you don't want to do at low volumes. And this circuit, this feedback path, tone shaping feedback path, is partly responsible for shaping the signal, the sound quality, or the sound richness, if you want to call it that these guys were trying to get when they designed this radio based on volume. Okay. And the next step is even more dependent on volume, but not at the output. It'll be at the input. Now, what I'm going to do is I'm going to do this. There are a few components to check. I'll be checking all these resistors, right? I will be replacing all these capacitors. So 1, 2, 3 capacitors. I'm not going to make you watch me desolder 3 capacitors and check the resistances of these components. If something is wrong with them, I will tell you next time. But for now, this is what I wanted to explain to you. The feedback path that is used to shape the tone coming out of your speakers. But nothing like this is really used in modern amps. Modern amps try and get the tone that you want before it actually gets amplified. Once the tone that you want is at the volume pot, they want a clean amplification. This is all but clean. This is distortion galore. This is distortion. It distorts the content that's coming out of your speakers compared to what's going in. Precisely because they wanted it to be distorted in a way that is pleasing to the ear, in a way that optimized the sound, the richness that they were trying to produce with these radios. Okay, that's where I'm going to leave you for now, because I'm sure that very few of you have actually stuck out to the end. If you have, thank you for your company. I had to stick it out, but you don't. And I hope you have enjoyed that. And if you have, please click like, share, subscribe, and all that jazz. And if you want to support the channel directly, you can do so on Patreon and PayPal. Links are in the description below. Once again, thanks for watching. Bye for now. And most of all, stay safe.